Alhamdulillah. Okay, everyone, let's begin then. So in the last session, we started probability. We covered all the concepts that we have in this topic. We started with the idea of probability. It's basically the chance of something happening. Normally, we talk about the chance of something in terms of percentages. But if you write that same number in decimals, we say that's probability, right? Probability is of favorable outcomes divided by the total number of possible outcomes. Possibility diagram, a two-dimensional table. So when we have two events happening at the same time, we can sometimes use this 2D table to help with our calculations. But when you have more than two events, what you do is you use a tree diagram to help with the calculation. We talked about this, how to make tree diagrams, and how to do calculations based on a tree diagram. On a tree diagram, in probability calculations, you need to remember, as you go horizontally along branches, you multiply probabilities, and vertically you add probabilities. Why? Because horizontally, there's an and between the events that, one thing is happening and another thing is happening, so you multiply those probabilities. And as you go vertically in a tree, there's an or between the cases. So it's either one case or another case or another case. We add those probabilities. That's what we talked about. We talked about the conditional probability. Of conditional probability, we discussed this in detail, but at the end, we had this formula that we can use to find conditional probability. Probability of A given B, that is equal to probability of A intersection B divided by probability of B. What that really means is, in the numerator, you have the probability of both events happening at the same time, and in the denominator, you have the probability of the given event. That's what we did. And then we talked about the concept of mutually exclusive and independent events. What are mutually exclusive events? These are events in which if one event happens, the other cannot happen. Or in other words, mutually exclusive events are events that cannot both happen at the same time, right? If one happens, the other cannot happen. If the second happens, the first cannot happen. How do you prove that two events are mutually exclusive? This is the idea that we use for that. If the probability of intersection is equal to 0, that means that those events are mutually exclusive. Do disjoint sets or the probability about independence not affect the other event, right? So if A happens, the probability of B remains unchanged, unaffected. If B happens, the probability of A remains unaffected, right? These are independent events. And the condition that we use to basically determine whether two events are independent or not is this, that probability of A intersection B, that should equal probability of A times probability of B if two events are independent. So this is the condition that we check for that. We looked at one example of this as well in the last session, in which we whether two the last have a look at some past paper questions. Now I can see some of the questions that you guys have posted. Let's start with some of them. Now, this worksheet does contain some questions that relate to some later topics. So some of the questions that you asked about, for example, question number 13 from the worksheet, that's this one. This is basically discrete random variables. So in the later topics as well, in discrete random variables, in binomial distribution, not the question probability. Okay, then you sample. It does not exactly require, but it can be done using combinations as well. That's the permutations and combinations concept. So the questions that are from later topics, we will not be able to do them today, but once we've done those topics later on, you should be able to figure these questions out later on as well. So question number 13, this is something that we cannot do right now. We will do this later on. Okay, but question 14, we'll have a look at that. Question 18 as well, this is expected that look at them later. But then the rest of them, let's try to do them. This one as well, question number 20. We can do the first 5 parts of this, but the last part is binomial distribution. So binomial distribution. So that is something that we will not be able to do. Is my voice lagging for everyone? Is my voice lagging for everyone? Okay, I'm sorry. Just let me check this. Okay, what about now? Is it fine now? Is my voice okay for everyone now? All right, good. So I was basically saying there are some questions in this worksheet that relate to later topics, discrete random variables in particular. So we will not be able to do them for now, but the rest of them we can do. For instance, question number 13, this is from discrete random variables. We will do this later on. Question number 18 that one of you asked about, this is also a later topic, discrete random variables. We will skip this as well. Question number 20, we can do the first 5 parts of this using the probability concepts. However, the last part, part 6, that's binomial distribution. Again, that's something that we will leave for later as well. Okay, so apart from these questions, we will have a look at the rest of the questions that you've asked about. Let's start with the relatively easier ones first. This is question number 23 from the worksheet. Let's have a look at this. Question 23 from the worksheet, let's try this. Okay, so it says box A contains 8 white balls and 2 yellow balls. Box B contains 5 white balls and X yellow balls. This is very similar to O-level probability questions, actually, the first few parts of this. But let's try this. We have 2 boxes. Box A contains 8 white balls and 2 yellow balls. 8 white and 2 yellow. And box B contains 5 white balls initially and X yellow balls. A ball is chosen at random from box A and placed in box B. A ball is then chosen at random from box B. The tree diagram below shows the probabilities for the colors of the balls chosen. Justify this probability X over X plus 6 on the diagram. Where does this probability come from? Now, how do we think about this? You see what's happening the first time? you have 8 white balls and 2 yellow balls in box A. What's the probability of selecting a white ball the first time? It's 8 out of 10, right? There are 10 balls in total. Out of them, there are 8 white. So 8 over 10 will be the probability of selecting a white ball. What about the probability of selecting a yellow ball then? That will be 2 over 10. Now, once you select a white ball, that ball is placed in box B. Okay, that white ball is placed in box B. Now, what happens when you place this ball in box B? Box B had 5 white balls earlier. 1 white ball is added to that. How many white balls do you get as a result of this in the second box now? Now the situation would be after this, in the second box, you would have 6 white balls. And what about the total? The total would be x plus 6. That's where this probability comes from. What's the working that you would show here? You would say the probability of getting a white ball the second time is going to be the numerator. It has 5 balls earlier, 5 white balls earlier. 1 white ball gets added to it. Okay, divided by the total number of balls in box B. Initially, the total number of balls in the second box was x plus 5. That was the initial number. 1 gets added to that, right? So you add 1 to the numerator and also add 1 to the denominator. Earlier, the probability of white was 5 over x plus 5 in the second box. When 1 white ball gets added to it, you have 1 added to the numerator and 1 added to the total in the denominator as well. And that simplifies to, okay, I'm sorry, we're talking about yellow balls. I'm sorry, not white balls. Sorry about that. I'll change that. What was the probability of yellow balls, of getting a yellow ball the second time? It was x over x plus 5. Okay, so probability of getting a yellow ball the second time, if these were the balls inside that, would be x over x plus 5, right? That would be the initial number, x over x plus 5. If this was the composition, 5 white and x yellow, x over x plus 5. Now, if 1 white ball gets added to that number, 1 white ball gets added to that number. Now, the number of yellow balls remains the same. That does not change. But the denominator, the total number, it has 1 added to it. So you say you have 1 added to the denominator, and that gives you x over x plus 6. So this probability at this branch should be x over x plus 6. The earlier calculation that we did, that was for white balls. So if this is the probability for yellow balls, what about the probability of getting a white ball the second time? That would be 6 over x plus 6. Because once you have 1 white ball added, the number of white balls becomes 6, and the total number is x plus 6. The total number is x plus 6. So this probability is going to be 6 over x plus 6. Similarly, we can complete the rest of the tree diagram as well. If you select a yellow ball the first time, what happens is the second box has 5 white balls. That was the number that we initially had. But then we had x yellow balls initially. How many yellow balls would we have now? There were x earlier. We have 1 added to that. Now we have x plus 1 yellow balls. What's the probability? What's the probability of getting a white ball the second time? That would now be 5 over the total number. What's the total going to be? X plus 6, right? This would be 5 over x plus 6. And getting a yellow ball the second time, that would be x plus 1, because there's x plus 1 yellow balls divided by the total number, which is x plus 6. This is what the tree diagram would look like. For the first part, if you want to write down an explanation in words, you can do that. You can say the total number would increase by 1. that is why the denominator is going to become x plus 6. Or you can show some working like this, that in the denominator, you clearly show that you have 1 being added like this, and that will be sufficient. For the second part, you don't have to give any reasoning. You just have to complete the tree diagram. There's no explanation that's required there. You can just write down these probabilities directly. Okay. Now I'll just repeat this for those of you who might be confused still. Remember the initial state. We have, I'll write full forms now. We had 8 white balls in box A, and we had 2 yellow balls in box A. In box B, the initial situation was we had 5 white balls and we had X yellow balls, right? That was the initial state. Now, if 1 white ball is selected from the first box and put in the second box, what happens is the number of white balls increases. So now we have 6 white balls and X yellow balls. What's the total going to be? X plus 6, right? So that's why these are the probabilities that we get. Probability for white, 6 over X plus 6. Probability of yellow, X over X plus 6. If we select yellow from the first box, the composition in the second box now becomes 5 yellow and the 5 white. So I'm not feeling well right now as well. I think that's increasing the careless errors that I'm doing. 5 white balls, and then what about the yellow balls? There were X yellow balls. We add 1 to that. It becomes X plus 1 yellow balls. What's the total that you have here? X plus 6. So probability of getting a white ball the second time, that's 5 over X plus 6. Probability of getting a yellow ball the second time, that's X plus 1 over X plus 6. That's where these numbers come from. Okay, so you complete this tree diagram. This is just for your own self. You don't necessarily have to write that anywhere. You can write these probabilities directly as well, and that will be sufficient. So that's what the tree diagram looks like. Now the next part says, part 3. If the ball chosen from box A is white, if the ball chosen from box A is white, then the probability that the ball chosen from box B is also white is 1 over 3. Show that the value of X is 12. If the ball chosen from box A is white. Now, what case are we talking about? We're talking about this case. From box A, we are selecting white. Now, this is something that is given to us, that from box A, we are selecting a white ball. All right. From box A, we are selecting a white ball. Given this, the probability that the ball chosen from box B is also white is 1 over 3. Now, we know that this probability is supposed to be 6 over X plus 6. They are telling us that the probability is 1 over 3. All we have to do is just equate those two numbers. 6 over X plus 6, that should equal 1 over 3. And you solve this equation, cross multiply, you get 18 equals X plus 6. The value of X turns out to be 12, and that's what we were looking for. Okay. Now, make sure that you understand the statement correctly. It says, if the ball chosen from box A is white, so we already know that we are at this point. Okay. Then after this point, what's the probability that the ball chosen from box B is also white? That is 6 over X plus 6. So we are only going to consider 6 over X plus 6 in this case. We are not going to multiply 8 over 10 with that. It's not going to be 8 over 10 into 6 over X plus 6. This is the probability of getting a white ball the first time and a white ball the second time. If you had to find the probability of getting a white ball the first time and getting a white ball the second time, that would be this. This is different. The statement that's given is different. It says, if the ball chosen from box A is white, so it's given that the ball chosen from box A is white. There's no probability involved in the first step here. We are already at this point, right? We have reached this point in the tree diagram already. Now, after that, what's the probability of getting a white ball the second time? That is just 6 over x plus 6. So we're just going to consider that. Is that okay? Make sense to everyone? So we just use x over x plus 6 here. Okay? All right, good. Now, let's look at part 4 now. By the way, I would recommend when you're asking questions that you send your question to everyone. Don't feel shy about it. It's all right. The benefit of that is everyone can see what question I'm answering. If you're sending a message to me directly when I'm responding to you, then everyone else might be confused. Okay, what was the question that you asked? So it'll be very helpful when you're asking questions. It's okay. There's nothing to feel shy about. Nobody's going to judge you for any stupid question. There's no stupid question. If you don't understand something, just say that. That's all right. If you send to everyone, I think that will be helpful. So everyone can see in the chat box as well. Okay, this was the question that I was basically responding to. Okay, that was part 3. X equals 12. That's the value that we get. Now it says part 4. Given that the ball chosen from box B is yellow, find the conditional probability that the ball chosen from box A was yellow. Whenever you see given that, understand they're talking about conditional probability. In this case, they've explicitly used this terminology as well. But even if they said, given that the ball chosen from box B is yellow, find the probability that the ball chosen from box A was yellow. That also means they're talking about conditional probability. All right. So what's the conditional probability that we're looking for now? Given that the ball chosen from box B is yellow. So what is given? Ball chosen from box B is yellow. That is given. And we need to find the probability that the ball chosen from box A was also yellow. Let's write down the conditional probability formula on this side. This was the formula, probability of A given B, that's equal to probability of A intersection B divided by probability of B. Or we can just understand this in words. In the numerator, we have the probability of both of those events happening at the same time. And in the denominator, we have the probability of the given event. Okay. Now, what's the probability that we're looking for here? Probability that the ball chosen from box A was yellow. Probability that ball chosen from A was yellow, given that ball chosen from box B is yellow. We can write it like this. Okay. What is this going to equal? Probability of the ball chosen from A yellow intersection. Intersection means and, basically that both of these conditions should be met at the same time. A should be yellow and B should be yellow. Divided by the probability of the given event. What is given? That B was yellow. That's what you have in the denominator. That's what the formula is going to look like. Now, you don't necessarily have to write it down like this. You can write down the numbers directly as well, the values directly as well, and that's perfectly okay. Let's look at the tree diagram. Yellow and yellow from box A and yellow from box B, right? Let's look at this probability first. What path do we have to follow on this diagram? Yellow, yellow. What is this probability? It's 2 over 10 times x plus 1 over x plus 6. Now we already know the value for x, right? We can input that value of x. The value of x is 12. So that's 12 plus 1 divided by 12 plus 6. We can simplify this and see what this gives us. 13 over 18. And that's 13 over 90, I think, right? 18 times 10 is 180, and then that gets cancelled. Yeah, 13 over 90, that's the probability that we have for this yellow and yellow. Okay. Then, okay, I'm sorry, just give me a second. I need to take a quick call. अभी क्लास से बेटा हो जी जी अच्छा okay, so that's what we are going to have in the numerator. In the denominator, we have the probability of the ball from the second box being yellow. Now, the second ball can be yellow in two cases. It can either be yellow here or it can be yellow here, right? These are two cases. We have to consider both of them. We have already found one of these cases. What about the other one? That you have white first and then yellow. Let's find this probability. It's going to be 8 over 10 times x, which is 12, divided by 12 plus 6. What do we get from this? 8 over 10 times 2 over 3. What would that be? Has anyone done this? Because that's 8 over 15. This number is 8 over 15. All right. And now we can input these values in that formula. In the numerator, we have the probability of both being yellow. That's 13 over 90. That's what we have in the numerator here. 13 over 90 divided by both of these cases. So we add them up together. It's either this case when the second ball is yellow or this case, there's an or between them. So we add these probabilities. In the denominator, we have 8 over 15 plus 13 over 90. Put this whole thing on your calculator and you get this conditional probability. What does this turn out to be? What's this number? Thirteen over 61. So that is the probability that we get from this. Okay, all right, thank you. That was part 4. That's conditional probability. This is how you would do that. Any questions on this? Any problems, anyone? No questions? Okay, let's move on. So that was question number 23 from the worksheet. Okay, so next one. 14. All right, let's do question 14 and question 3. Okay, let's do this one and then we do 14 after this. Question number 3. Okay, so it says data about employment for males and females in a small rural area are shown in the table. A person from this area is chosen at random. Let M be the event that the person is male and let E be the event that the person is employed. Now, whenever you have a table given in a probability question, the first thing that you should always do is total the rows and total the columns. Add row totals and column totals, right? Add these numbers here, add the totals. What is 206 plus 412? That is 618. 305 plus 358, that should be 663. 206 plus 258, 564. And then these two numbers, they add up to 717. And then the grand total. What's the grand total? 1270, no, 1281. Okay. Add these totals, first of all, and that they will help you with your calculations. Always do this whenever you have a probability question in which you have information given in the form of a table. Now they're saying a person from this area is chosen at random. You see there are 1281 people in total now. We have that total number. So a person is chosen at random from these 1281 people. Let M be the event that the person is male and E be the event that the person is employed. Find the probability of M, the probability of that person being male. What is this probability going to be? How many total males do we have? 618 out of how many? 1281. So probability of selecting a male, if you were to select someone randomly, is going to be 618 divided by 1281. You can see if this can be simplified. 618 divided by 1281, and that simplifies to 206 divided by 427. That's the probability that we were looking for in the first part. Okay, so once you add those totals, it becomes fairly straightforward after that. Now, the second part says, find the probability of M and E. What does that mean? The case when both of these conditions are met, M and E, okay, male and employed. You are selecting one person randomly from these 1281 people. What's the probability that that random person is both male and employed? Where can we be in this table? This number 412, that represents that, right? Male and employed, that's 412. What will be the probability? 412 divided by the total, which is 1281. Again, you can see if this can be simplified. 412 divided by that. No, it cannot be simplified. So that's the final answer, part 2. Again, fairly straightforward. Now it says, are M and E independent events? Justify your answer. Are these independent events? What was the condition for independent events? Do you remember that? Independent events, when are two events independent? The condition for that was A intersection B should equal probability of A into probability of B. If that condition is met, then that means that they are independent. Now, A intersection B, that's basically the same thing as saying A and B, okay? Where A and B both are true at the same time. Let's check that. Let's see if that condition is met or not. So in this case, the events are M and E. So we can say probability of M intersection E, that should equal probability of M times probability of E. If this condition is met, they're independent. If they're equal, then they're independent. If they're not equal, then they're not independent. Let's check that. Intersection probability, we have already found that's 412 over 1281. We already have that number. Probability of M as well, we have found that in the first part, that's 206 over 427 times probability of E, probability of some randomly chosen person being employed. What's that? Let's calculate that. The total number of employed people is 717. Divide that by 1281. That's the probability of a person being employed. 717 divided by 1281. Right? Now you have to figure out whether these two numbers are equal or not. Let's simplify the right-hand side. 206 divided by 427 times 717 divided by 1281. Okay, that's giving me some decimal answer. 0.2700. Okay, what about the number on the left side? 412 divided by 1281. This is 0.3216. These two numbers are not equal. Since they are not equal, we say they are not independent. Okay, if these numbers turn out to be equal, we would say they're independent. Okay. That's the third part. That's the standard rule that we have for independent events. If the probability of their intersection is equal to the product of their individual probabilities, then they're independent. If that's not the case, then they're not independent. All right. That was part 3 of this. Let's move on now to part 4, which says, given that the person chosen is unemployed, find the probability that the person is female. Now, this is conditional probability, right? This is conditional probability. Given that the person chosen is unemployed, right? So whenever we have given something, that means it's conditional probability. Find the probability that the person is female. Now, how do you write that in conditional probability notation? Given is that the person is unemployed. That's a given. Probability that we have to find is that they're female. Female given unemployed. Okay, that's what we are looking for. What should that equal? Probability of F intersection, or you can say and unemployed, divided by probability of what is given, probability of unemployed. That is going to give you this number. Okay. That's one idea that you can use, and that will give you the result. Okay. So you can find the probability of intersection, divide that by probability of unemployed. Now I'll do it that way as well. But when you have a table given, it's actually much easier to do it directly from the table without even using the formula, if you understand the logic correctly. What are they saying? Given that the person chosen is unemployed. Given that the person chosen is unemployed. What does that mean? It has to be one out of these 564 people. So we know that the person is unemployed. So that means it has to be someone out of these 564 people. So that's the total possible outcomes. That should be the denominator in this probability. Out of this 564 number, how many are female? What's the probability of somebody being female? That's 358. You can write this probability directly like this if you have information given in a table like this. Okay, so it will be 358 divided by 564. You could write down this answer directly from the table. That's your probability. That's one way of doing this. Alternatively, you could use that formula that I wrote above. You could use the standard formula. Probability of F given unemployed equals probability of F and unemployed divided by probability of unemployed. How do you do this calculation? F and unemployed, female and unemployed. What's that box here? What's that number? Female and unemployed. That's this number. 358 out of how many? 1281. So what will be the probability of somebody being female and unemployed? It would be 358 divided by 1281 whole divided by probability of unemployed. What is that going to be? Probability of unemployed, that's 564 divided by 1281. 564 divided by 1281. And you see what happens? 1281 and 1281, they get cancelled anyway, and you get the same result that you had on the left side. 358 over 564, and you can simplify that to see what that gives you. 358 divided by 564, and that simplifies to 179 over 282. That's the probability that we were looking for. Okay, now let me repeat this. When you have information given in the form of a table, it's always easier to use the table for your probability calculation directly without using any formulas. In this case, what are they saying? given that the person chosen is unemployed. So we know that the person that we are talking about is unemployed. So the person has to be one out of someone out of these 564 people. So that should be the denominator of your probability, right? 564 should be the denominator. Out of these 564, what's the probability that the person is female? 358 over 564, that's the probability. But right, that's a quicker and easier way of doing this. If you want to use the formula, that's the other possibility. In all the other cases, if we don't have a table given, for example, if we have a tree diagram, in that case, we prefer using the formula. In this case as well, you could use the formula, and that would work like this. We are looking for the probability of female given the person is unemployed. In the numerator, we would have probability of F intersection UE, and in the denominator, we'll have probability of UE. Now, what's the probability of intersection when both conditions are met? This is where both conditions are met, 358. So the probability in the numerator would be 358 divided by 1281. That's what we have in the numerator. In the denominator, probability of unemployed, that's 564 over 1281. 1281 and 1281, they get cancelled, and we get the same result that we had there, and that's the probability that we get at the end. Okay, does it make sense to everyone? Oh, so that was question number 3 from the worksheet. Let's move on to the next one. Next, we want to do question 14. Question number 14. Okay, let's try this one now. Okay, take a minute, read the question statement, and then we'll discuss it. Three friends, Rick, Brenda, and Ali, they go to a football match, but forget to say which entrance to the ground they will meet at. There are 4 entrances, A, B, C, and D. Each friend chooses an entrance independently. Okay, independently means that whatever one person chooses, it does not have any impact on another person choosing that same entrance or not choosing that same entrance. So all of them are choosing one entrance independently, and apparently they don't have it. They don't have their phones with them. Maybe it's Pakistan where they don't have any signals there, so they block cellular networks in that region for security measures, so they can't contact each other. Probability that Rick chooses entrance A is 1 over 3. The probability that he chooses entrances B, C, or D are all equal. Okay. We have probabilities for Rick there. Brenda is equal likely to choose any of the 4 entrances. The probability that Ali chooses entrance C is 2 over 7. The probability that he chooses entrance D is 3 over 5. Okay, let's write down all of these probabilities. They've explained the probabilities in statements here. Let's write down the numbers from them. That will make it easier for us to do our calculation. So we have 3 people, Rick, Brenda, and Ali. Let's write them down here. So we have Rick, Brenda, and Ali. These are the 3 people that we have. And there are 4 entrances that are possible, A, B, C, and D. What are the probabilities that we have for Rick? The probability that he chooses entrance A is 1/3. So this probability is 1/3. Probability that he chooses entrances B, C, or D are all equal. So now the remaining probabilities equally divided amongst the other three entrances. Now, what's the remaining probability? This was 1/3, right? Total probability is 1. You subtract from 1/3. What does that give you? That gives you 2/3. Now, this 2/3 has to be equally divided amongst these three options. Okay. How do you divide 2/3 in 3? You'll say 2/3 divided by 3, that's 2/9, right? So that will be 2/9, 2/9, and 2/9. These are the probabilities for entrances B, C, and D. Make sense? Brenda is equally likely to choose any of the 4 entrances. That means 1 out of 4 is the probability for each entrance. For Brenda, 1/4, 1/4, 1/4, and 1/4. These are the probabilities for Brenda. And then finally, the probability that Ali chooses entrance C is 2/7. Okay, so this is 2/7. Probability that he chooses entrance D is 3/5. So this is 3/5. And for the other 2 entrances, the probabilities are equal. So what we do again is we find the remaining probability. 1 minus 2/7 minus 3/5. What do you get from this? You can put this on your calculator directly. 1 minus 2/7 minus 3/5. And that gives us 4/35. That's the remaining probability. Now, this remaining probability has to be equally divided amongst the remaining 2 entrances. 4/35 divided by 2, that will be 2/35, right? So that means the probability of entrance A is 2/35 for Ali, and for B as well, it's 2/35. So these are all the probabilities that we have. Once you have listed down all the probabilities like this, now it will make it easier for you to understand what to do after this. It says find the probability that at least 2 friends will choose entrance B. Okay, now how do we think about this? Probability that at least 2 friends will choose entrance B. At least 2 friends, that means we will have to make cases for this. Okay. One possibility is that Rick and Brenda, they choose entrance B, and Ali does not choose entrance B, right? And then Rick and Ali could choose entrance B, and the other Brenda might not choose entrance B, and so on. We would have to consider the different cases that we can have. Now, let me write down those cases. How should I list them so it becomes easier to understand? Let me think about it. We're talking about entrance B, right? Okay, so let's say we've got Rick, Brenda, and Ali. These are the 3 people that we have. One possibility is that Rick chooses entrance B, Brenda chooses entrance B, Ali does not choose entrance B. So B complement, that means not B. Okay. Another possibility would be that Rick chooses entrance B, Brenda does not choose entrance B, and Ali chooses entrance B. Then another possibility would be that Rick does not choose entrance B, Brenda chooses entrance B, and Ali chooses entrance B. And these are 3 possible cases that we could have. Are these the only cases? Are we missing something? These are cases when 2 friends will choose B. Is there any other case that might be possible as well? It says at least 2 friends. That means it's also possible that all 3 of them choose B. That's another possibility as well, right? It's not exactly 2 friends choosing B. At least 2 friends have to choose B. That means another possible case could be that all the 3 friends, they choose entrance B. So that's another possibility that we have, that all of them choose entrance B. That's the 4th possible case. So we have these 4 cases that are possible. We can find the probabilities for all of these 4 cases and add them up together, because it's either the first case or the second case or the third case or the 4th case. There's an or between these cases. So we will be adding these cases together. Let's find the probabilities for each one of these cases one by one. The first case, Rick chooses B. What's the probability for that? 2/9. So we say it's going to be 2/9 times 1/4 for Brenda. And then Ali does not choose entrance B. The probability of Ali choosing entrance B is 2 out of 35. What's the probability of him not choosing entrance B? 1 minus 2/35. What would that be? 33 out of 35. That's this first case, right? Basically, you can add all of the other cases. That's one possibility. That will give you 33/35. Or an easier and quicker way is subtract from 1 this probability. 1 minus 2/35. And that gives you 33 out of 35. These probabilities are going to be multiplied. Why? Because there's an and between them. So the first case is that Rick chooses entrance B and Brenda chooses entrance B and Ali does not choose entrance B. There's an and between them. Okay? So we multiply these probabilities. Then the second case is Rick chooses entrance B, that is 2/9. Brenda does not choose entrance B. Probability of choosing B is 1 out of 4. Not choosing B, what would that be? 3 out of 4. And then Ali chooses entrance B. That's 2 out of 35. That's the second possible case. Again, there's an and between these three events. Rick chooses B, and Brenda does not choose B, and Ali chooses B. Okay, there's an and between them, so we are multiplying them. Then third case, Rick does not choose B. Choosing B has probability of 2/9. Not choosing B would be 7 out of 9. And then Brenda chooses B, that's 1 out of 4. And then Ali chooses B, that's 2 out of 35. Can someone please do these calculations for me and let me know what the results are? The third case is all of them choose B. That means we have okay. All of them choose B. That's 2/9 into 1/4 into 2 out of 35. These are the 4 cases that we get. What are the results that we get? The first one is 11/210. And the next one, 1/105. What we'll do is we will simplify this. Okay, yeah, so let's do it like this. The denominator is 9 times 4 times 35. That is 1260. So let's do it this way. That will make things easier. The denominator is 1260 for all of them, right? 9, 4, and 35. These are the 3 numbers that are multiplying in the denominator. The numerator in the first case is going to be 66. In the second case, it's going to be 4 times 3, that's 12. And the third case, the numerator is 14. And in the fourth case, the numerator is 4. And then you add these cases because it's either the first case or the second case or the third case. And that is going to give you the final result. You can see what that is. Numerators, they add up to 66 plus 12, that's 78. 78 plus 14, 92. 92 plus 4, that's 96. 96 over 1260. You put this on your calculator now, and you would get the simplified form for this. That is 24/315. That's the probability that we were looking for. That's our final result. Okay. Okay, why do we have to consider Ali's not case? I'm not sure if I understand your question correctly. One thing that I can think of is that you're saying we could combine the first case and the last case. We could merge them into a single case. Yes, that might be possible, although that might be confusing for most people. But you could merge first and last cases by just finding 2/9 times 1/4, and that will give you the total of this and this. But then the other two cases, you still have to find separately. You can't merge all of them into one, if that makes sense, Ibrahim. Okay, let me...
Sir, I'm asking why do we need to include the case जिसके अंदर वो B में नहीं जा रहा? Why can't we just use it like जो B में जा रहा है उसको ले जाएं और जो नहीं जा रहा उसको exclude करके फिर answer कर लें?
Okay, so you are saying in the first case, for instance, if we want the probability that at least 2 friends will choose B, we say, okay, find the probability that that Rick chooses B and Brenda chooses B, and then don't care about Ali choosing B or not choosing B. Is that what you're saying?
Yes, sir.
Okay, the problem with that would be, if you say Rick chooses B and Brenda chooses B, you find this probability and you don't apply any condition to Ali. That is going to give you 2/9 into 1/4, and that will give you some number that's 2/36, which is 1/18. But then you consider another case in which you're saying Brenda chooses B and Ali chooses B, and you multiply those probabilities, let's say. Or let's consider the second case. In the second case, we actually did this. 2/9 for the first one, and then 2/35 for the last one. Is that what you're saying? Okay. Now the problem with this would be, similarly, you could do the third case and fourth case like this. In the first case, if you're saying Rick chooses B and Brenda chooses B, and then you do not apply any condition to Ali. That means in this first case, Ali could have gone through gate B or he could not have gone through gate B. Both of those possibilities are there in the first case. The first case includes both B, B, and not B. And it also includes B, B, and B, right? Because Ali could have gone through entrance B or he might not have gone through entrance B. So the first case includes both of these possibilities, this case and this case. And now you look at this one. In this, you have specified that Rick chooses B and Ali chooses B, but you've not specified anything for Brenda. That means this can include both this case when Rick chooses B, Brenda does not choose B, and Ali chooses B. That's one possibility, but it also includes the case that all of them choose B. It also includes this case. So this case where all of them are choosing B, it will be counted multiple times. It will be counted in the first case as well. It will be counted in the second case as well. So your probability would be overestimated, right? It will come in every single case. If you think of a tree diagram, it will look like this. Rick chooses B or not chooses B, and then Brenda chooses B or not chooses B, and then Ali chooses B or not chooses B. This is what the tree diagram would look like for this case, with the first step showing Rick, second showing Brenda, and the third showing Ali. So the possible cases are that all of them choose B, or the first two choose B and the third does not choose B. The first chooses B, second does not choose B, third chooses B. The first does not choose B, second chooses B, and third chooses B. These are the 4 cases that we're considering. We do have to consider what happens for each of them. We can't just skip one of them because in that tree, we have 3 steps. We have to multiply 3 probabilities like this. Does that make sense? Okay. All right. Now, if anyone of you got confused with what are we talking about here, forget about this. This is what we have to do. Okay. This is what you would have to actually do here in part 1. Let's look at part 2 now. Now, part 2 says, find the probability that 3 friends will all choose the same entrance. They will all choose the same entrance. Now, let me just copy this here. The probabilities that we had. So we have them in front. These are their probabilities. What's the probability that all of them will choose the same entrance by coincidence? What would that be? All of them choosing the same entrance. Now, one possibility is all of them choose A. Another possibility is all of them choose B, or all of them choose C, or all of them choose D, right? So what would that be? You would say probability of all of them choosing A. That is going to be 1 over 3 times 1 over 4 times 2 over 35, right? 1 over 3 times 1 over 4 times 2 over 35. That's the probability of all of them choosing A. The second case is all of them choose B. That will be 2 over 9 times 1 over 4 times 2 over 35. The third possibility would be all of them choose C. That is going to be 2 over 9 times 1 out of 4 times 2 out of 7. Plus all of them choose D. That's 2 over 9 times 1 over 4 times 3 over 5. We're multiplying them because we're saying Rick chooses A and Brenda chooses A and Ali chooses A. That's one case. Or the second case is Rick chooses B and Brenda chooses B and Ali chooses B. So we multiply these. Similarly for the rest of them, and then we add all of them because it's either this first case or the second case or the third case or the fourth case. So we add all of those cases up, and that is going to give us the final result. That's it. That's the second part is pretty straightforward. That should give you the result. Okay. You can make a tree diagram if you want. Although I think making a tree diagram here will require some thinking as well. So a lot of people end up getting the structure wrong. So it has to be like this. If you show all entrances, that will become too big. So you can't make a tree diagram like this showing A, B, C, and D, because then the tree diagram becomes very big, right? 4 times 4 times 4, it will become 64 branches at the end. So you can't show all entrances here. You'll have to make it concise like this. Since we're only talking about entrance B, you would make a tree diagram like this. That will be more efficient. That is either B or not B. It doesn't matter what the other gate is, what the other gate selected is. We just care about entrance B. It's either B or not B. If you make a tree diagram like this, yes, that might make sense. And you can do that first part using this tree diagram as well. Okay, for the second part, tree diagram, I'm not sure if it's going to be very helpful. You can just do it directly like this. What's this number? Has anyone done this calculation? If not, I'll just move on. You can do this on your own and you'll get a result from this, okay? Any problems? Any questions, anyone? No? All right, let's move on then. So another question that one of you have asked about is 2 out of 35, is that the final answer? Okay, so this results in 2 over 35. Okay, so let's look at the next one now. Okay, so there's no other question from the worksheet, it seems. Batul has asked a question from May, June 2017. Where was that? Let me find that. Okay, May, June 17, paper 6 to question 4. Yes, Navya, sure. You can make tree diagrams for this. You can make 3 separate tree diagrams. That will work. As long as it works, that's fine. It's just about uh, trying to be more efficient with your time in the exam, because 75 minutes is not that long, even though in S1, time is generally not a problem. But still, you don't want to end up spending too much time on one question, so that you don't end up leaving too little time for maybe another question at the end of the paper. So it would not be very efficient if you make those tree diagrams, but it works. Yes, logically that makes sense. You can do that, and that will be fine. Okay. Okay. Let me do 2 more questions now. So you're saying question number 11, part 2 from the worksheet, and then May, June 2017. Let me see if I can find that in this worksheet. May, June 2017. Paper 6-2, question number 4. Is it this one? Batul, is it question number 33?
Yes, it's the 33.
Okay, yes, I'll be posting this worksheet as well. I just need to split this into multiple files, and I'll do that. Hopefully this weekend, I'll be doing this as well. 33, right? Okay. Let me see if it involves any other concept, discrete random variables. It doesn't look like it. We could do it without that. Question number 33. From the second worksheet, I'll be uploading this worksheet as well. You can do more practice from this. It has more recent questions as well. I haven't posted this yet because you did not have a lot of time yet to do these questions, but I'll be posting it hopefully by tomorrow, and you can work on this over the weekend as well. Tomorrow we are starting permutations and combinations, by the way, and that's going to be an extremely important session, because all the other topics, all the other concepts of permutations and combinations, they're going to be dependent on tomorrow's class. If you miss tomorrow's class, next week is going to be difficult. The next 4 classes are going to be on permutations and combinations. And tomorrow is going to lay the foundation for the next classes. Please make sure that you're there and you are focused, because that's the most difficult topic that you have in S1, and arguably across all 4 papers, it's one of the most difficult ones. I would rate it at a similar difficulty level with integration and complex numbers. In terms of concepts, it's not that much, but when you look at the questions and permutations and combinations, you will find that they require a lot of thinking and a lot of practice. So tomorrow is going to be the first class on that. Please make sure that you are there. 2 identical biased triangular spinners with sides marked 1, 2, and 3 are spun. Okay, so we're spinning 2 spinners. They have their sides marked 1, 2, and 3. For each spinner, the probabilities of landing on the sides marked 1, 2, and 3 are P, Q, and R respectively. The score is the sum of the numbers on the sides on which the spinners land. You are given that probability that the score is 6 is 1 over 36, and probability that the score is 5 is 1 over 9. We need to find the probabilities, find the values of P, Q, and R. Okay, now that looks like a good one. What I can do is I can try to make a triangular spinner. Let's say it looks something like this. And okay, now the probabilities are not the same. So let's just draw it randomly. So let's say we have 1 here, we've got 2 here, and we've got 3 here. So we are spinning this, and then we have some probabilities of the spinner landing on 1, 2, and 3. We are given that the probability of 1 is equal to P, probability of getting 2 is equal to Q, and the probability of getting 3 is equal to R. Now there are 2 spinners that we are spinning, okay? And then the score is calculated as the sum of the numbers on which the spinners land. Probability of 6 is equal to 1 over 36. Now, how many total possible outcomes can we have? When we are spinning 2 spinners, both of them have 3 sides in total. We are doing 2 things at the same time. It might help drawing a 2D table for this calculation. That will make things much simpler to basically list down all the possible outcomes, first of all. What are the possible outcomes of scores that we can have? Let's represent them on the side here, the possible scores that we can have. On one spinner, you can have 1, 2, or 3. On the other spinner, you can have 1, 2, or 3. The score is calculated by adding these numbers. So we have 2, 3, 4. And we have 3, 4, 5, 4, 5, 6. All right, these are the outcomes that we can have. These are the 9 possible scores that we can have. Now, the probability of getting a score of 6 is 1 over 36. Okay, so probability of getting a score of 6 is 1 over 36. When can we get a score of 6? Score of 6 is when both the numbers give us 3. Now, keep in mind, all of these outcomes do not have equal probabilities. They do not have equal probabilities. So you can't find probabilities like this. You can't say that the probability of getting a score of 6 is equal to 1 out of 9 because this is 1 out of the 9 possible outcomes. That would be wrong because these are biased spinners. These are not fair spinners. All the outcomes do not have the same probabilities. Okay, so we can't do number of favorable outcomes divided by total number of outcomes directly on this because the probabilities are not equal. Okay, so that will not work. Keep that in mind. That's an important point to understand here. But what are we given? Probability that the score is 6 is 1 out of 36. Now, what does that mean? Score of 6 can be obtained. Score can be equal to 6 if the outcome is 3 and 3. You get 3 on the first spinner and you get 3 on the second spinner. What's the probability that the score is 6? If we have to write it in probability notation here. Score is going to be 6 if you get 3 on the first spinner and you get 3 on the second spinner. That is going to be probability of 3 times the probability of 3. What's the probability of 3? That's R. R times R, that should equal 1 out of 36. And that gives us 1 out of 36 here. R squared equals 1 over 36. And that's going to give us the value of R first of all. R equals 1 over 6 from this. This is the probability of R first of all. Probability of 3 first of all. Probability of getting a 3, that is equal to 1 over 6. That's one thing that we were given. Then we're given that the probability of getting a score of 5 is 1 over 9. Now, when can we get a score of 5? Score of 5 can be obtained when on one spinner you have 2 and on the other you have 3, but there are 2 possible outcomes. You can have 2, 3, or you can have 3, 2. Right? There are 2 possible cases that we can have for this. Okay, so there's a question that why are we multiplying these R's? Let me write it like this. Probability that the first spinner gives us 3 and the probability that the second spinner gives us 3. Only then the score can be equal to 3, right? That the first spinner gives us 3 and the second spinner gives us 3. The probability of 3 is R. For both the spinners, R times R, right? So that gives you R squared. Makes sense, right? Okay, good. Okay, now score being 5, the probability of that is 1/9. Now, when can you get a score of 5? Probability that score is equal to 5. There are 2 possible cases that you can have for that. Let me write them down in full so that it becomes clear. One case is that on the first spinner, you get 2. And on the second spinner, you get 3. That is one possible case. That's this case, for instance. At 2, you get 5. At 2 and 3, you get 5 score. The second possibility would be that on the first spinner, you get 3, and the second, you get 2. That can also give you a score of 5. So that's another case that you consider. Probability of having 3 on the first spinner and having 2 on the second spinner. What does that simplify to? Probability of first spinner giving you 2, that is Q. Probability of second spinner giving you 3, that is R. So we have QR plus probability of first being 3, that's R, times Q. Second being 2, that is Q. And that simplifies to 2QR, right? QR and RQ, they're the same thing, so it becomes 2QR. And they've given us that this probability is supposed to be 1/9. So we equate this to 1/9. Now we already know the value for R, that is 1/6. We can put this here, 1/6, and that is going to give us the value of Q, which is 1/3. That's the value of Q that we get. The value of Q is 1/3. All right. Now, once we have the values of R and Q, the third possible outcome is 1 that has a probability of P. All of these probabilities should add up to 1, right? So we can say P plus Q plus R should equal 1. And that's going to give us the value of P as well. You can see what that is. 1 minus 1 divided by 3 minus 1 divided by 6. And that will give you the result. The value of P turns out to be 1/2. That's the value of P that we were looking for. Okay. Now, it's not necessary to draw this table. It's just for your own ease. If you want to do that, you could do it without the table as well, right? Just think of it in your head, the cases that you can have for getting a score of 6 and 5. If you want to make a table, you can do that as well. But that's how you would approach it in terms of working. This is what you would have to do. Does this make sense to everyone? It was quite tricky, to be honest. Very different from the normal questions that you see in probability. Okay. All right, let's do one last question then. That's question number 11, you're saying, and then we end with that. More questions like this. I'm not sure you'll find many like this in probability. You will see more questions like this in discrete random variables later. Let me see if I can find one. So I haven't seen many like this in past papers. Let me see if I can quickly find one like that. Not really. What I'll do is I'll upload this other topical as well, and you can have a look at this. And if there are any questions from this as well, you can always post on the WhatsApp group, or we can discuss them towards the end of one of our classes later on as well. No, so you'll not find many questions like this in the worksheet or in past papers. This is very different from the normal questions that you see in probability. Okay, let's do question number 11. How we find P? we have three possibilities, right? P, Q, and three probabilities, P, Q, and R. The total probability has to be 1, right? So if we know if we know Q and R, then P is just going to be 1 minus the other ones, right? Okay, let's do question number 11, and then we end with that. So now this is one of the most difficult questions that you will see in past papers on probability as well. Not all of it, but I think one part of this at least. It's only difficult because making the tree diagram is difficult. Once you make the tree diagram, then the rest is kind of okay. Question number 11. Okay, so this is the last one that we're doing. All right, so it says, in a television quiz show, Peter answers questions one after another, stopping as soon as the question is answered wrongly. You might have seen TV shows like this, right? In our times, we used to have 𝗣𝗀𝗀𝗿𝗶𝗹, and internationally they have others as well. I'm not sure if there's one these days going on. I don't watch many TV shows anymore, so I'm not sure, but you might have heard of these quiz shows. So you have this show in which Peter is answering questions, and he stops as soon as he gets one question wrong. Okay, so he loses, or the game stops as soon as he gets one question wrong. The probability that Peter gives the correct answer himself to any question is 0.7. The probability that he gives the wrong answer himself to any question is 0.1. And the probability that he decides to ask for help for any question is 0.2. So in questions like these, there are, in quiz shows like this, there are some lifelines that they have that they can ask the audience, they can call a friend to answer some question and things like this. And that's what it means to ask for help. On the first occasion, they're saying that Peter decides to ask for help, he asks the audience. On the first occasion that Peter decides to ask for help, he asks the audience. The probability that the audience gives the correct answer to any question is 0.95. The information is shown in the tree diagram below. You can see that here. Show that the probability that the first question is answered correctly is 0.89. So you have the tree diagram given in the first part already. What's the probability that he answers the first question correctly? Now, the first question can be answered correctly two ways. He can either answer the first question correctly himself, or he can ask for help, and then the audience answers the question correctly, and then he gets the question correct. So there are two possible cases that we can have here. This is 0.7, and this one is going to be 0.2 times 0.95. So we add these two cases, 0.7 plus 0.2 into 0.95, and that will give you the result for the first part. So that's fairly straightforward. The first part is not that tricky. 0.7 plus 0.2 into 0.95, and that's 0.89. That's the probability that we get from the first part, 0.89. Let's look at the second part now. It says on the second occasion that Peter decides to ask for help, he phones a friend. The probability that his friend gives the correct answer to any question is 0.65. Find the probability that the first two questions are both answered correctly. Now, this tree diagram that you see here, it's only for the first question, right? It's only for the first question. Now, we would have to extend this tree diagram first so that it extends to two questions. How can we do that? If the first question is answered wrongly, the game stops there, right? That's how the game works. If he gets a question wrong, the game stops. Okay, so we don't have anything coming after this. But then if he gets the question correct, what are the three options that are going to be there? For every question, he can give the correct answer himself with a probability of 0.7. So we can say he can answer the question correctly himself. Let's denote it like this. Peter answers the question correctly himself. So PC, okay? This is the probability of 0.7. Another possibility is that he answers the question wrong himself. That's 0.1. That's Peter wrong. And the third possibility is that he asks for help. Peter asks for help. What's the probability for that? That's 0.2. Now, when he decides to go for help, now this is the tricky part here. This is what is important to understand. When he decides to ask for help in this case, what is the probability that he gets the question correct? And what is the probability that he gets the answer wrong? What are these probabilities going to be? Anyone? Probability of getting this question correct. What are the probabilities in these branches going to be? Probability of being correct and probability of being not correct. Given these statements, it says the probability that the audience gives the correct answer to any question is 0.95. And in the first equation that Peter decides to ask for help, he asks the audience. That was one thing that we were given. On the second occasion that Peter decides to ask for help, he phones a friend. The probabilities are 0.95 and 0.65 respectively. What is the probability of being correct here going to be? Now remember, you need to understand the question statement correctly. It says on the first occasion that Peter decides to ask for help, he asks the audience. Now, in the context of this game, what has happened is, in the first step, he got the question correct himself. For the second question, he is asking for help. Is it the first time that he's asking for help in this game until now? Yes, it is the first time, because the first question he answered correctly himself. So he's asking the audience in this case. When he goes for help, he's not asking a friend, he is asking audience, right? Because this is the first time that he's asking for help, because he got the first question correct himself. So he's asking the audience, what's the probability that the audience gives the correct answer? That's 0.95. And the probability that the audience gives the wrong answer, that's 0.05. Okay. Then what about this case? In the first question, if he asked for help, one possibility is that the audience gives the wrong answer. In that case, the game ends there. If the audience gives correct answer, then the game continues. And for the second question, he again has three options. He can answer the question correctly himself or wrongly himself, or he can ask for help. This is 0.7, 0.1, 0.2. But now that he decides to ask for help, he has already asked the audience before. He cannot ask the audience again now, right? So now, the second option is, on the second occasion that he asks for help, he phones a friend. So now his friend is going to be answering the question. Now the friend can either be correct or he can be wrong. What are the probabilities of the friend being correct and wrong? 0.65 and 0.35 respectively. This is what the tree diagram is going to look like. Once you've gotten this tree right, then it's not that difficult. Now we want to find the probability that the first two questions are both answered correctly. What is the probability going to be now? When are the two questions answered correctly? One possibility is that he answers correctly himself the first time and also answers correctly himself the second time. That's one case. Or he can answer correctly himself the first time. he can answer correctly himself the first time. And then the second time he asks for help and the audience answers correctly. That's the second option. The third option is the first time he asks for help and the audience gets the question correct. And the second time he answers correctly himself. And the fourth option would be the first time audience answers correctly. And the second time he asks for help again and the friend answers correctly. So he's totally dependent on help. In this last case, these are the four possible cases that we have. We find these four probabilities, add them up together, and that is going to give us the result. The first case is 0.7 times 0.7. That's the first case, 0.7 times 0.7. That is when he answers correctly himself both times. Now, it often helps when you have a conditional probability question. Next, it often helps to label these probabilities. That will be helpful in the next part. So I'll be labeling them like this. These are probabilities that Peter answered the question correctly himself both times. That's one case. Or the second case is he answers correctly himself the first time. And then the second time, he asks for help and audience answers correctly. He asks for help and audience answers correctly. That's the second case. So that will be 0.7 into 0.2 into audience answering correctly. That's 0.95. That's the second case. Or the third case is he asks for help the first time. Then the audience answers correctly. And then the second time, he answers correctly himself. What are these numbers going to be? 0.2 into 0.95 into 0.7. And then the fourth option is he asks for help and audience answers correctly. And then he asks for help again and the friend answers correctly. Right, that's the fourth option. That will be 0.2 into 0.95 into 0.2 again into 0.65. And that is going to give you the result. That's 6 marks. And that should give you the result. Yes, Reza.
Sir, I'm a little bit confused about the, I think the fourth possibility, because in the question it says that on the second occasion he asks for help, he phones a friend, but the probability that we've used, this is the first time he's asked for help. Jiski probability is 0.2.
In the fourth case?
Yes.
No. So look at this. The first time he's asking for help and the audience answers correctly. This is the stage that we're at. Now he has already asked the audience in the first question. And now he is going to the second question. So he has already asked the audience before, right? So now it's the second occasion that he's asking for help. So now the second time he asks for help, it is going to be from the friend.
Right. So it doesn't matter what his first occasion or what he did on the first occasion, right?
Yes, it does matter, because if he answered correctly himself the first time, then he has not asked for help yet. And this is the first time that he's asking for help in the second case that we had, right? That's the first time that he's asking for help. In that case, he would ask the audience. But in this last case, since he has already asked the audience before, for the second question now, it will be the second occasion that he's asking for help. So now he'll go to friend in this case.
Right. Okay.
Okay.
Mm-hmm.
All right. Now, let's just add up all of these probabilities. 0.49 plus, what is this going to be? 0.7 into 0.2. It's a 6-mark question. I would recommend that you do show another step. So even if you do a careless error somewhere, you get more partial marks. Okay, so I'll recommend showing this step, that you do these calculations separately. First, 0.7 into 0.2 into 0.95. That's 0.133 plus. This is the same numbers, right? So this will also be 0.133. And then 0.2 into 0.95. No, 0.2 into 0.95 into 0.2 into 0.65. And the last one is 0.247. Add all of these numbers up and that will give you the total probability that you're looking for. That's 0.7807. That's the second part. Okay. Now let's look at the last part. The last part says, given that the first two questions are both answered correctly. Given that, now that's conditional probability. Given that the first two questions are both answered correctly, find the probability that Peter asked the audience. Remember conditional probability formula? I'll write that on the side. A given B, that is equal to probability of A intersection B. That means both events happening at the same time, divided by probability of B. Right, that's the conditional probability formula. Now, what exactly are we looking for here? Let's write down the formula. Given that the both questions were answered correctly. So what are we given? Both questions were answered correctly. That's given. What's the probability that Peter asked the audience? Probability that he asked the audience. That's what we're looking for. Given that both were correct. Okay. Now, what is this going to be equal to? Probability, using the formula, that he asked the audience and both questions were answered correctly. That's the numerator when both conditions are met. And in the denominator, you have the given case in which both are correct. That's what the formula is going to look like, right? Now, what's the probability that both questions were answered correctly? We already found that in the previous part. That's 0.7807. That is going to be your denominator, that both are correct. Okay. And now the numerator is that he asked the audience and both were correct. Now, these are the four cases in which both answers were correct. Right? These are the four cases. In how many of them he asked the audience? In which of them he asked the audience? He asked the audience in this case. Right? He asked the audience in this case as well. He asked the audience in this case as well. So apart from the first case, he asked the audience in the remaining three cases. You can see it in the tree diagram as well. He asked the audience in the second case, the third case, and the fourth case. Right? So what we can do now is in the numerator, we would have these three probabilities added. Okay? The fourth probability is 0.247, 0.0247. Okay, I'm sorry about that. Okay, so I just used the calculator value, so that's why I think the final answer is still correct. 0.49, 0.247. Yeah, it might be the case. 0.2 into 0.95 into 0.2 into 0.65. Okay, that's 0.0247, sorry. This number is 0.0247, but I used the calculator value for the last one, so I think the final answer is still going to be correct. Okay, now, the numerator is when he asked the audience and both questions were correct. These are the three cases in which both conditions are met. So that is going to be your numerator now. 0.133 plus 0.133 plus 0.0247. That's the numerator. You can evaluate this and see what that gives you. That is 0.3723 or 0.372. Can somebody confirm this as well? 0.372. That's the probability that we're getting for the second part, for the third part. That's the conditional probability. Okay, and that's it. That was a 10-mark question. The main complication was getting the tree right. Okay, once we have that correct, then the rest is just standard tree diagram calculations. They're not that difficult. Okay, no problems. So that's it for today then. Tomorrow we start permutations and combinations. We will get done with most of the major concepts tomorrow, inshallah. So please be there. Do not rely on recordings. Live classes are going to be more beneficial because you can ask questions as well. So that is going to be more helpful. Okay, so that's it for today. I'll see you again in the next class. Everyone who wants to leave, you're free to leave. I'll be here for a few more minutes in case anyone has any individual questions. Ibrahim, as usual, has a few, I think. Yes, Ibrahim. Okay, Allah Hafiz, everyone who was leaving. Yes, Ibrahim.
अस्सलाम सर।
वालेकुम अस्सलाम।
सर वो क्वेश्चंस है ना, मैंने अभी आइट्रेशन के करने हैं और डिफरेंशियल इक्वेशंस के थोड़े से न्यू वर्कशीट से। तो मैंने आपसे ये पूछना था कि मतलब P3 की क्लासेस तो होनी ही, तो मैं S1 के एंड पे ही आपसे पूछ लिया करूँ।
हाँ, S1 के एंड पे पूछ सकते हो, ठीक है, या आप WhatsApp पे कर सकते हो। If you be patient enough to wait for my responses, if not, आप स्टार्ट्स के बाद कर सकते हो।
मैं आपको भेज दिया करूँगा ना, और अगर आपकी क्लास रात को हुई और आपने रिप्लाई ना दिया तो तब तक फिर मैं आपको फिर आपसे पूछ लिया करूँगा।
ठीक है, सही है, नो प्रॉब्लम।
और सर मैंने आपको एक और बात भी बतानी थी कि आई गेव माय वीज़ा इंटरव्यू ना, तो वो एक्सेप्ट हो गया है।
अच्छा, माशाल्लाह, आप इस पे परेशान थे।
हाँ,
ओके, दैट्स गुड, अल्हम्दुलिल्लाह। अल्लाह ताला बेहतर करे इंशाल्लाह आपके लिए।
ओके सर, अल्लाह हाफ़िज़।
Congratulations, माशाल्लाह।
थैंक यू सर, अल्लाह हाफ़िज़।
अल्लाह हाफ़िज़।